The file format used by CasaXPS is the ISO standard, which is also referred to as the VAMAS format, and data can be converted to this format from other formats using the Convert to VAMAS File dialog window. In this specific directory there are a set of PXT files, and this is a binary format that is generated by a Scienta Omicron system, and it includes spectroscopic data as well as additional context data in the form of comments. So when a PXT file is selected using the Convert to VAMAS File dialog window and then the Open button pressed, the data are converted and a new VAMAS file is created, and it is written back to the original directory. So here is the VAMAS file that has been created by selecting this particular PXT file. The file is opened within CasaXPS, so we immediately see the VAMAS file that was just created. Information that was within the data file can be displayed if we enable a display option that includes the acquisition parameters. And within these acquisition parameters we can see that these data were measured using a synchrotron source and a photon energy of 150 electron volts with a pass energy 10, the step size of 0.01, and that the analyzer, the operator and the beamline are indicated in this last line here. And these can be seen and edited using the dialog window that is available from the View menu. So we can see the analyzer, this is the Scienta Omicron analyzer, the operator, so if you wanted to update the operator and include the first name, the beamline, perhaps we want to indicate that this is the beamline, and then press OK, and we can see that this information is now updated within the acquisition parameters. There are other parameters within the PXT file that are useful when displaying data and understanding the data. In this case, the experimental variable that has been defined for this VAMAS file is indicated as a slice, and the term slice in the context of the Scienta Omicron data indicates the way the data have been collected from the multi-channel detector. So we have a single slice that has formed these data, where the slice relates to the partitioning of the detector. And then another parameter that can be displayed over here is the sample identifier, and if we use the edit mode button to switch between the experimental variable and the sample identifier, we can see that this was a particular sample from which this silicon 2p doublet has been measured. The context for data is always useful. In this case, because this is a Scienta Omicron analyzer and we've got a beamline, then one of the things we ought to work out is the relationship between noise and the signal within these data. And this is important when we want to construct a peak model. We need to have a target for our figure of merit, and in order to work out what that target should be, we need to consider the data itself and not simply assume that we're aiming for unity, which you might expect for purely pulse counted data. We can make an assessment of the noise variation by adding a region to these data, and if we create a region on a background interval and then specify a background type that calculates a line that fits the data in a least squares sense, then observing the variation of the data about this line gives us an indication of the residual standard deviation. So this is the figure of merit that we'll use when we fit data using components and backgrounds. So if we achieve a residual standard deviation of 2.4 when we fit components and a background to these data, then reproduction of the data is compatible with the noise that we're seeing in these data. So it is not necessary to achieve a residual standard deviation of unity, because that would be unachievable for these data. So let's fit these data now and see how well we can do. So I'll take a copy and we'll prepare a peak model that is basically going to be a line shape and background for the one of these peaks in the silicon 2p. So this is the silicon 2p 3/2 peak. If I create a background and I make this a linear Shirley. Then I introduce some of the Shirley shape, then I'll offset this a bit and introduce a line shape, which is an asymmetric line shape, and I've prepared this earlier so that when I fit these data I end up with a fit which is clearly a residual standard deviation that is suggesting that we do not have good data reproduction. However, if I now introduce a shape that will be based on a linear approximation which can be fitted at the same time as the component, this will be fitted on top of the Shirley background together with this asymmetric peak, and I end up at this point with a line shape, a background shape, and a residual standard deviation which is improved, but it certainly is not the target residual standard deviation. So I'm going to now introduce a few more adjustments. I'll do that by adjusting the background, and when I adjust the background and then say fit, we end up with a residual standard deviation that is 2.8. So this is much closer to what the target residual standard deviation ought to be for these data. I'll just make a few display adjustments for the display of this peak model, and this allows us to see the line shape sat on top of the background. So this is a reasonable data reproduction. The residual standard deviation for the most part looks uniform. You can see that there's some deformation here and here, but for the most part it looks uniform, and the residual standard deviation is very close to the target residual standard deviation that was calculated for the data. But the most remarkable thing about these data is the full width half maximum for this silicon 2p 3/2 peak. The energy resolution is quite stunning and far beyond what you would expect for a lab-based XPS instrument. When we measure silicon using a lab-based instrument, then the X-ray source alone would prevent a full width half maximum of about 0.08, which is the case for these data here. And even for a monochromated system, the full width half maximum is about 0.26 eV. So this is the spread of energy of the photons arriving at the sample. So a full width half maximum of 0.08 would be beyond a system that relied on a mono based on an aluminium anode.